Professor Tim Persoons is an associate professor in the Department of Mechanical Manufacturing Biomedical Engineering at Trinity College Dublin and a visiting faculty in the NSF Cooling Technology Research Center at Purdue University. He completed his PhD in Mechanical Engineering from KU Leuven in 2006. He is a recipient of the Marie Curie International Mobility Fellowship of the IRIS Research Council, hosted by the School of Mechanical Engineering, Purdue University, for the year 2010. His research deals with fluid mechanics and control of convective flows for enhanced sustainability in electronics cooling and energy system integration. He has authored more than 100 publications in peer-reviewed journals and conferences.
Thank you very much for a kind introduction. I believe you can all see my screen here, so I'll kick off. So the topic of my talk today here for this workshop, and again I apologize for not being there in person, but it's a pleasure to be here with you remotely from Dublin, Ireland. The topic is convection and flow control for electronics cooling and energy system integration. What I'll do is I'll first give a brief introduction on the work, and the work that I'll present here is work that was done by two of my former PhD students and two postdocs over the last roughly 5 years or so. The work was focusing primarily on the situation in Ireland, where we have a lot of data centers that have penetrated the electricity grids in the last 10 years or so. So we're in a bit of a unique situation worldwide in terms of prevalence of data centers. They're presenting a lot of challenges for the stability of our electricity system. And the topic of the talk here is to go over a few different aspects where we could improve their integration into our energy system. And even though the focus might be on Ireland, initially at least, there are some lessons that we can learn, for the situation worldwide as well. So here's the outline of my talk. So again, I'll give a brief introduction on the data center situation in Ireland first. We'll talk about some of the fundamentals of heatsink design and how we might improve the cooling of servers in data centers, so that it's easier to deal with waste heat recovery afterwards. And then we'll go over a few selected topics, not in a lot of detail, but I'll provide some references if you're interested, and we can talk about it afterwards if there's any questions on any of the particular topics. We'll first start by looking at some implementations of liquid cooling for CPU and GPU cooling, and then some air-liquid hybrid cooling implementations afterwards. So here's the brief overview of the situation in Ireland in terms of the chart on the bottom right there shows the energy consumption, electricity consumption since 2020, and then the projection over the following 10 years. And as you can see, a large chunk of that is taken up by the red bars, which represent data centers. So last few years or so, we have about 14% of our national electricity consumption, which is going into data centers, which is probably the highest worldwide, maybe apart from a few exceptions, like maybe Singapore or so. But for countries of the size of Ireland, this is quite exceptional. And it presents a lot of challenges. There's a lot of pushback from the public. Policymakers are very much aware of that nowadays, and there's actually a temporary halt on new data centers being allowed into the market. So roughly 75 are currently in operation, 30 are under construction, but there's a lot of debate at the moment about, should we get more of these facilities in? They present a large contribution in terms of economic benefit, of course, to the country, but it's being harder and harder to keep this sustainable. So for the moment, these are primarily a so-called drain on the energy system. And we're looking at ways, can these be integrated more in the energy system? And a logical way, of course, would be to look at the cooling of these systems, and perhaps also to make use of waste heat and couple these systems, with local heat clients, which could be hospitals or it could be domestic, it could be commercial buildings. Yeah. So this all is in the context of some government action. So since 2021, we have the Climate Action Plan, which is sort of a roadmap for how we will go to decarbonization of the energy system. So the goal here is by 2050 to reach net zero emissions. So net zero CO2 emissions. That should be. So in that context, we're looking at data centers because they're so prevalent and they contribute something like 14 up to maybe 30% of the national electricity consumption. So there is a lot of room there to play with the data center sector, so to speak, to help us reach that goal. And so we're seeing, or the government is seeing data centers as a way to control energy consumption to some extent. And of course, there's not just the consumption, but as you install a data center, there's also backup power that's installed typically with these systems. So there's large, battery banks. There's backup power diesel generators that are installed as well. So, and then of course there's the question of can we reuse some of the waste heat that's produced by these large scale electronic systems, and could that be linked to local communities so that they could benefit from data centers being present in the community. So the slide here just shows the current state of affairs, and next talk by Professor Poulikakis will also, I'm sure, deal with some of these things as well. So the dominant cooling mode at the moment still for data centers is air cooling. There's a lot of talk about liquid cooling, etc. But for the most part, and especially again for the case in Ireland, 99% of these data centers are air cooled. And that means that the delta T, so the temperature difference between the coolant outlet temperature and the ambient, is very minimal, something like 5 to 20 degrees Celsius or so. So in terms of coolant to be used for waste heat recovery, that's basically useless energy, right? So we need to be able to increase that delta T. And that's where other technologies like liquid cooling or hybrid air-liquid cooling or immersion cooling could come in to increase that delta T and be able to do something more with that waste heat. And that could take various shapes. You could reuse the heat as is, whether it's commercial or residential buildings, for instance, or maybe industry or horticulture. These things could be coupled, and there's some examples of successful implementations of coupling a data center with, for instance, greenhouses, where you could grow tomatoes or something like that next to a data center and reuse the waste heat in that form. Or you could think of converting it to cooling. Maybe not so important in our climate over here in Ireland, but there's other cases where that could be important, or even converting it into electricity. But for all of these cases, and even this direct reuse of heating, we really need to increase the delta T here. And so that's what the focus of some of our work is about. So if you look at what is generating the heat in these data centers, these are some schematic diagrams of servers that you would find in these systems. You typically have multiple CPUs per server. The heat sinks are removed here, so we're just looking at the sockets over here, and so you have the DIMM modules, the RAM modules on the sides. Those are the horizontal bars that you can see there, and then in the middle you have 2 or sometimes 4 CPU sockets. Sometimes what's not shown here, you sometimes also have GPUs more and more nowadays when, as AI becomes more and more prevalent, these things tend to run on GPUs rather than CPUs. But generally speaking, this is roughly what it might look like. Most of the heat is dissipated in the CPUs or GPUs, and then the RAMs represent sort of a quarter of the total heat dissipation. So the challenge here is that it's quite a non-uniform heat distribution, right? The CPUs are quite small. They represent about 3/4 of the heat dissipation. The memory modules are more distributed. So their air cooling is probably more appropriate, and liquid cooling is typically seen as more appropriate for CPUs, perhaps. So in a so-called hybrid air-liquid cooling scenario, typically what we mean by that is that the CPUs would be liquid cooled, and then the memory modules and all the rest of the components would still be air cooled. And so that means if you're following the airflow through the system, the air flows from left to right, is being pushed by chassis fans through the system. The air will gradually pick up heat as the coolant travels through the server. And so locally, you will see a slightly different temperature in the first CPU and in the second CPU. So typically, more downstream, you would have, higher air temperatures, and therefore the memory modules towards the end of the server, for instance, and the second CPU in the topper case there, where you have the series coupling of two CPUs behind each other, the second CPU would see slightly higher temperatures as well. And you can have different configurations. You could have parallel flow or a combination of parallel and series flow. So, and typically, of course, these things, the cooling systems here, the heat sinks are designed for optimal reliability of the electronic systems. And so the question is, can we change the heatsink design here so that we can make better use of waste heat? So schematically, a Sankey diagram would show, where the energy flows are in a typical data center. On the left here, you have an air-cooled data center, and metrics that you may be familiar with if you read literature on data centers are the so-called power utilization effectiveness, or the PUE factor, which is essentially the ratio of the total power consumption of the system divided by the power consumed just by the IT equipment. Right, and then in addition, you have the cooling infrastructure, which in an air-cooled data center can be anywhere up to 30-40% of the total power consumption, depending on the type, right? But then all of that energy effectively is dumped in the form of low-grade waste heat dumped in the atmosphere. So with the use of liquid cooling, what we can do is slightly change the balance here. And then there's a few things that will happen. The PUE value will typically drop, which is a good thing. The cooling infrastructure will take up, less energy, but primarily you will now be able to partly, never completely probably, but partly recover some of the waste heat and reuse that in a different part of the energy system. So traditionally, electronic systems, like I said, are, the design goal, the requirement there was reliable operation. They didn't really care about waste heat recovery. And so that means that the operation typically means that the fan flow rates are generally high. So you want to limit the component temperature and ensure that everything stays cool enough inside. And the chassis fans then in that case provide a dual function. And we'll come back to that, later on. The fans, in fact, they push air through the system. They provide obviously the advection, so they carry the heat from the server and into the room where it's then dumped eventually in the atmosphere. But they also provide the local cooling. And so what we want to do want to slightly move away from that for a waste heat recovery scenario where we still want, of course, the operation to be reliable, but we want to increase the coolant outlet temperature so that we can make better use of that heat. So that means that we want to lower the fan speed slightly so that, in balance, your outlet air temperature goes up. And we want to reach a situation where the server chassis fans only advect heat from the server, but that local cooling is dealt with by other means, which could be liquid cooling, or it could be some adaptive local air cooling. And I'll show you some examples of what that might look like in this presentation. So we'll take a brief look at just the fundamentals of heatsink design before we look at some of those more implementations of cooling systems in data centers. So if you start with just a very classical heatsink design, and if you have certain constraints that are available, certain heat dissipation, certain maximum temperature for the chip, let's say in our case, and a certain air temperature that you have available, then there's a few design parameters that you have to play with if you're designing, for instance, a plate fin heatsink, as shown schematically in the diagram there. You have, of course, the fin spacing is the typical design parameters, right? So I've indicated that with DH there, the hydraulic diameter. You have maybe the total volume that you have available, so that gives some indication of the lengths of the heatsink then, in combination with the hydraulic diameters. And then if you're designing this for optimal so-called thermodynamic design, you might look at something like minimizing the entropy generation rates, right? So, which is essentially the sum of two components. One is due to the heat transfer that occurs. So I've indicated that with S sub H over here. And the other one is S sub F, which relates to frictional losses. So the sum of those two, if you minimize those, then you typically have an optimal design. And what I've done here, not in a lot of detail, but I've tried to break it down into the component parts, right? So some of the things are constraints and things that we can't control, things like the thermal constraints, the power dissipation, etc. Those are assumed to be givens. And then we have freedom to change things like the hydraulic diameter, for instance, and to some extent we can change Nusselt numbers and things like that as well. So if you carry this through and you break it up into the effect of design parameters, so the components that you have control over, then you have the fluid properties, which typically are beyond your control, right? It's either air-cooled or liquid-cooled. For the most part, it'll be air-cooled, so that's kind of fixed. And then you have thermal constraints that are, givens that you don't really have control over. So if you just look at the design variables only and their effect on SH and SF, this table here is sort of a summary of what happens with heatsink design. So for instance, the effect of the fin spacing or the hydraulic diameter, the H in this case, if we go to a denser heatsink, right? So DH will go down. That means that SH will go down, which is good, but we get a penalty for additional pumping power, and we see an increase in SF, right? So if you look at the first column over here, this balance between SH and SF will lead to an optimal fin spacing if we just look at that aspect, for instance. So that's kind of a trivial. But if you look at the effect of Nusselt and the friction factors, obviously we want to increase the Nusselt number because that decreases SH, and we also want to decrease the friction factor, which would decrease SF. But the problem is that, of course, with the well-known Reynolds analogy, these things tend to be coupled. So if you increase heat transfer, you typically also pay a penalty and increase pumping power. So, better designs of heat sinks and of cooling systems for servers, if we bring it back to a server, better designs will try to decouple those two things. So for a server, that means that we want to decouple the advection, the moving of fluid through the system, from the local cooling enhancements. So we want to separate those things out to some extent, so we have more control over the system. Right. So we'll have a look at a few example implementations. So first of all, we'll look at some liquid cooling implementations. And this first example looks at combining pulsating flow in liquid-cooled cold plates for CPUs. So we want to control, through varying the pulsation properties, so things like amplitude, frequency, but also the waveform. We can control the heat transfer rates within these systems, and this will allow us more localized control over the cooling performance in servers. And again, the end goal here is always to increase the coolant outlet temperature while still maintaining safe operation. And of course, in a server, there's always going to be fluctuating heat loads, right? Depending on the computational load that is demanded of a certain system, you might see spikes or reductions in heat loads. And so the goal here is to come up with a control mechanism to be able to deal with those things locally on a CPU by CPU level. So the research here and the link below there shows a paper if you're interested in reading up more on this particular topic. The research was primarily experimental, so we have a micro particle image velocimetry setup over here as shown. So basically consists of an inverted microscope. Laser light is introduced at the back, and then we have a high-speed camera that is visualizing the flow inside of a microchannel heatsink. Yeah, I don't think there's anything else here that I have to cover, but just, the field of view here is something like 1 by 1.5 millimeters. So we're looking at a small segment of a cold plate here, and then visualizing the flow inside the system so that we can quantify the velocity flow rate. What's kind of special here is that we have this pulsator device. So if you follow the flow loop, basically, you have a gear pump over here, which imposes a steady state flow through the system. From the gear pump, the flow goes through a mass flow meter, and then either through a pulsator or directly into the test section over here. Across the test section, we're measuring, of course, temperatures inside. We measure the flow velocity with the micro PIV system. And then there's a pressure sensor, a delta P sensor, to measure the pressure drop over the test section. And then the flow returns to a reservoir and then back to the gear pump. But the pulsator here is unique because it allows us to superimpose an oscillating component onto the steady flow. And we have control with that pulsator, which is shown schematically over here. We have control over both the amplitude of oscillation and the frequency of oscillation, and we can also change the waveform of oscillation. So the flow comes from the gear pump basically through this little pump chamber and then back out and goes into the test section afterwards. And again, more details are available in the paper if you're interested, or we can discuss afterwards perhaps. The test section itself is quite basic. It's effectively just a single microchannel. So we have 0.5 millimeter in width, 1 millimeter in height, 25 millimeters long. And this is basically our test section. We have a cartridge heater and then some thermocouples so that we can also look at the heat transfer performance. And what we've looked at is to see, well, first of all, the effect of amplitude and frequency has been studied in other cases. What we wanted to look at is the effect of waveform, and are we able, just by changing the waveform, can we have some control over heat transfer rate, and are we not paying too much of a penalty in terms of pressure drop? So what we did is we looked at symmetric waveforms and then skewed sines in the two directions, as well as triangular waveforms. And what you see here is just a sample of the velocity distribution. So this is for the animation that you're looking at here in the bottom right-hand corner is for this case, which is a skewed sine. So compared to the pure sine, the velocity distributions in the microchannel, for a pure sine, they look, they exhibit the expected behavior. This has been well documented. This is nothing new. But then if you change the waveform to a triangular wave or to a skewed sine, you suddenly see that you have much higher gradients at the wall in some of these phase angles. And this is not only seen in the flow velocity, but we can also see this in the heat transfer performance. So this is how we skew the sine with a continuous variation of this parameter theta over here. So if theta varies between -1 and 1, you effectively go from a skewed sine, forward skewed to a rear skewed sine. And if theta is equal to 0, it reverts back to a normal sine. And so the goal here was to have theta be the control input for this feedback control mechanism based on the live heatsink temperature as the thermal load is varying. So what you see over here is what happens if the power cycles between 90% and 100%, which is the green line over here. And the response without a control is that the apparent Nusselt number will change, of course, because of the thermal inertia in the system. But then as we enable our control, And this is done for this case over here for a frequency of 25 hertz. And we're effectively going from a steady flow to a pulsating flow. We can see that we have effectively an enhancement of the Nusselt number. And so, we don't really care too much about the absolute magnitude of the enhancement here. We care more about the fact that we have some control, some additional control over the heat transfer rate. And as we switch from steady flow to a pure sine at 25 hertz or a skewed sine at 25 hertz, you can see here the effect on the wall temperature in the heatsink, and also the effect on the Nusselt number as we go through these changes in waveform from one to the next. So that in itself is interesting. Another thing that we've looked at is microvalves. So this would be, again, for liquid cooling, a way to have additional control over the local convection inside of microchannels. And we've looked at various different things, but I just want to focus on one particular thing here, which was presented at a Terminic workshop in 2019. In which case we use shape memory alloy microvalves. So these SMA valves, they basically change shape in response to local temperature. So as the temperature of the heatsink exceeds a certain threshold temperature, these fins, if you will bend slightly and will affect the flow field. So we looked at this experimentally and also with some CFD, but that's described in a different paper. And I'll just show you a sample of what that looks like. So the idea here is as the heatsink heats up under an increasing thermal load, these microvalves can change shape, and that can affect the pressure drop in the system. So more flow can be sent through a particular microchannel to compensate for that change in temperature. And so this allows for a completely autonomous valve response. There's no external control required here. These things, actuate themselves, basically, depending on the temperature that they're sensing. So this could also be an interesting way to deal with non-uniform heat load and also transient heat loads. So in summary, for liquid cooling, there's multiple other things that we could have, looked at, but just looking at pulsating flow and adaptive microvalves, we have some new ways of controlling these flow fields. And so the goal here is enhancing the Nusselt number, being able to lower the flow rate through these systems so that the coolant temperature maximizes, and we're still able then to control the convection locally so that we can safeguard reliable operation of the electronics. So next we'll look at air cooling, right? So if in the assumption that liquid cooling takes over the CPU cooling, there's still some residual heat that has to be mitigated, from the memory modules, for instance. So again, typical server layout like this. So we have the DIMMs, which are the memory modules. We'll focus on those for the air cooling, and then the CPUs we assume are covered by liquid cooling. And so the goal here is to increase the outlet temperature of the air at the outlet of the server over here. And the assumption then is that downstream of this, we have a heat exchanger where we can extract the heat from the air and bring it into a liquid stream. And the goal here is to aim for both a high temperature at the outlet, but also a uniform temperature at the outlet to maximize the performance of the heat exchanger. And again, like we mentioned, for a typical server, there are no fans inside here. There are just fans upstream of the CPU, heatsink, and the DIMMs. And so these chassis fans basically have that dual function of both pushing the air through the system and carrying the heat, with the air that passes through the system, but also taking care of the local cooling. So what we want to do is to break up that coupling slightly, and deal with the DIMMs separately with air cooling. So we took a reference server, an Intel server, because we were working with Intel at the time. So this particular server here has chassis fans, and this kind of setup with two CPUs, one after the other. We instrumented this with a delta P sensor and a flow meter, so we could basically do a simulation in CFD and Fluent, and compare our CFD model to the measured delta P and the flow meter results. So we did remove the heat sinks here from the server. So the assumption is once you liquid cool the CPUs, that frees up a lot of space, a lot of empty space then becomes available in the middle of the server. And so if you don't do anything else, and you just have the fans pushing air through the system, most of the air will just bypass the DIMM modules and go through the middle basically, which is now empty space because the CPUs are liquid cooled by very small cold plates that don't really exhibit a lot of resistance for the airflow. So, logically, what you want to do is to have some baffles here so that you redirect the airflow to go mostly through the DIMM modules. And so that's what this research was all about, is finding the optimum shape of the baffles inside to maximize waste heat's recovery potential. So just, schematically, this is what our numerical setup looked like. It's a 2D simplified model. So we're just looking at the DIMM modules, and we have a heat flux boundary condition on the chips of the DIMM modules. Cell count is intentionally quite low, right? So 700,000 elements here. We did, of course, check for mesh refinement and things like that. But we want this to be a very efficient model because remember, this is a numerical optimization, right? So we have to run multiple hundreds and hundreds of simulations of various different shapes. So this model, can be very, very complex. So we've chosen for a 2D model, the omega SST turbulence model. And so the validation here shows that we're actually, even though it's just a 2D simulation, we're actually quite close to the pressure drop for the actual system if you compare it to the experiments. So this gave us some confidence that we would be okay to just use a 2D simulation here. And we've considered 3 different baffle geometries, baffle 1, 2, and 3 here. Various different dimensions that we could optimize. And so it essentially becomes a shape optimization problem then. It's a multi-objective optimization problem. So we're using multi-objective genetic algorithms to do this kind of optimization. But again, the benefit of this approach is that with the baffles, even though they're quite simple, they're cost effective, obviously, to implement, and we can do this in a retrofit scenario. So we could actually go to one of our industry partners and say, look, here's an existing system. We can take out the heat sinks from the CPUs, replace them with liquid-cooled cold plates, and introduce a few baffles that could be 3D printed or could be, made in some other way to improve the waste heat recovery potential of this particular rack, for instance. So the optimization problem is to look something like this. So we want to both ensure efficient cooling of the system, as well as improve the waste heat recovery potential, right? So on the efficient cooling side, we want to obviously limit the maximum component temperature. So we have some limit there. We want to minimize pumping power. And so this combination here is what we were talking about earlier in the heatsink design. So the sum of these 2 components will lead to an optimum heatsink design in terms of efficient cooling. But of course, we want to do more, right? We want to enhance the waste heat recovery potential. So we want to maximize the outlet temperature and also its uniformity so that if that air flows over a heat exchanger, that we're more easily able to extract the heat from the system. So it's a combination effectively of EGM, so entropy generation minimization, with a MOGA algorithm. And so that MOGA algorithm, the fact that you have multiple objective functions, means that you won't get a single optimal solution, but you'll get a Pareto front, right? You get multiple different potential optimum solutions, depending on what you decide is the dominant objective. And so from the baseline case, for instance, you're looking at the velocity magnitude here on the right. So from the baseline case, if you introduce a baffle, that means that you're channeling more flow through the DIMMs, which is what we want to do. And what it also means is that you're able to then reduce the velocity magnitude, right? So if you look at the sort of typical velocity magnitude initially in the baseline case, it's maybe something like 2 meters per second. You're able to reduce that quite a bit to something like 1 meter per second, maybe, because now you're cooling these DIM modules much more effectively. And of course, we also want to look at the shape of the baffle downstream, because we want to pull open the flow over here and make sure that we have a uniform distribution of flow that goes over the heat exchanger at the rear of the server. So if you look at some of the temperature plots from these numerical simulation results, you have again the baseline where, of course, the air flows over the DIMMs over here, picks up heat, and then you have a local hotspot in the outlet temperature. And for the most part, the heat, the air basically just bypasses the DIMMs, goes over the center of the server here, and just exits at the same 300 Kelvin that it came into the server. 300 Kelvin, by the way, is the inlet temperature. And then as you introduce baffles, you're able to pull open this profile and increase the uniformity of the profile, and also increase the average temperature of the profile. So you're doing two things, right? We can reduce the fan power, we can reduce the flow rate through the system. And by doing that, we're increasing the outlet temperature, but we're also increasing the outlet temperature uniformity. So that's just another representation of the same thing here. So just in the interest of time, I'll move over to our final topic here, which is the introduction of active local cooling. So being able to increase the cooling performance locally by some adaptive local cooling method, even in the air cooling case, can be very beneficial. So if we think back to the same configuration from before, where we have the two DIM banks, if you will. So the first one is the upstream bank. This one is typically very well cooled, right? Because it sees the fresh air coming in. But then the second bank has more difficulty in maintaining temperature below the threshold of the components, because of course the air is already preheated when it comes into this second DIM bank. So what we propose here is to introduce one single synthetic jet cooler in any of these four locations. So we won't have four, but we'll have just a single one, either between these DIM modules or here or here or here. And we look at a simple optimization for, similar to what we had before with the baffle in the middle, so that we can, channel most of the flow to go through the DIM modules, and we get this additional cooling effect of a synthetic jet cooler. And the synthetic jet cooler that we decided to model was one that's developed by General Electric, or now taken over by Avid Thermalloy. The so-called dual cooling jet. So it's a synthetic jet which basically is two flexing membranes. You have two piezoelectric actuators that are oscillating these two membranes, and that will cause a synthetic jet to form at the outlet of this slot over here. So the graph over here represents experimental results from a previous paper by Peter de Bock, where we have an indication of what the output velocity is for this jet at a particular operating condition, and superimposed with a solid line over here are our simulation results. So it's not a perfect match, but again, this is just a 2D equivalent of this jet. So we're basically looking at a 2D slice in this way. We're modeling this with dynamic meshing. And this is essentially the result that we get. So it's not perfect, but it's close enough that we deem that this is equivalent. And then later work looked at doing away with the transient simulation that we needed to simulate this synthetic jet to a steady state equivalent, which is this paper here in IEEE DCP-MP. So sample results here, and these are velocity contours at first. So on the left, we have no synthetic jet. So again, the baseline geometry with the empty space in the middle. And then the modified geometry, still without a synthetic jet, but with a baffle here to channel the flow through these systems, through the DIM banks, apologies. And then over on the left, on the right-hand side here, we have the same baffle, but then with a synthetic jet either in the middle here or a jet over here in this location. And so we were looking to, again, maximize the uniformity of the flow and the outlets, and also improve the cooling performance in the second dim bank. So effects, for instance, on the outlet air temperature here. So from the baseline temperature profile here, we can see that we're able to improve the performance quite a bit. If you look at the average outlet temperature here from the baseline case, by placing a synthetic jet in that fourth location. So if I just go back here, that's this location, in fact. This proved to be most effective in our case because it also helps make the flow more uniform by having this kind of Coanda effect, if you will, downstream of the baffle here. So we're able to get a good improvement of the average temperature at the outlets. The flow is reduced by 50% approximately. And also our uniformity is okay. I mean, it's never perfect, right? You still have some non-uniformity, but this was apparently the best combination in our view. So as a result, if you look at the whole approach of both passive cooling, so just using baffles, or active cooling, combination of baffles and that synthetic jet actuators, we're able to reduce the inlet velocity quite a bit while still making sure that the components are cooled sufficiently. So that means that we can increase the outlet temperature, and we are also improving the uniformity of the outlet temperature, which is also useful for waste heat recovery. And so the added benefit of having the synthetic jet actuator is that you can further improve these numbers, but you also have more adaptive control possibility, of course, because again, if the server goes from 100% utilization to a lower utilization, all of those thermal loads will change. And if you have some local components, for instance, that synthetic jet actuator that you can either enable or disable, or you can modulate the cooling performance somewhat, then it gives you more flexibility to trim out those differences and those modulations. Okay, so that sort of concludes my presentation. So I'll end with this summary here that, there's quite a lot of technological challenges here to deal with, but it also provides a lot of opportunities for very interesting research work. What we find challenging is that there's a lot of stakeholders involved. Data center operators are typically not willing to share a lot of information from how they do their business. So we only have a few partners that we were able to really make inroads with and convince of some of these things. And I think the main conclusion here that we can draw is that there's not a single cooling solution. You can't say liquid cooling will solve everything. There's always going to be a portfolio of approaches that we will need to consider. And also, what tends to be overlooked is that being able to retrofit existing systems is a big benefit, right? So if you can come up with a cooling system where you don't have to start from scratch and you can just go into an existing system, which has a huge investment cost, of course, associated with it, and you can retrofit these cooling systems, that's of huge benefits. Okay, so I'll end there, and I'll just thank my sponsors and PhD students and postdoctoral researchers, and happy to take any questions.
Yeah. So let us give an applause to Tim and take any questions from the audience here. Yeah.
Hello. I'd like to ask. Hello. Am I audible, sir?
Yeah, you're audible.
Yes.
So you are using microchannel heatsink for this cooling of processes. Then my question is that in microchannel heatsink, the characteristic dimension is very small. So in numerical analysis, you have done turbulence model. So usually the flow is laminar. So can you elaborate on this aspect?
Yes, that's a very good point. So for the simulations that I was talking about here, these are air simulations, right? So this is inside of the server. So we're not talking about the microchannel cooling aspect over here. So the last part of the talk was on the residual air cooling. So we're assuming that the CPUs are already liquid cooled. But the remaining flow in the server is still turbulent flow that is generated by the chassis fans. So the simulations that I was referring to here in ANSYS Fluent, they are in fact turbulent flow simulations. What I haven't talked about is the numerical work that we've done on the liquid cooling. So we have looked, again with Fluent at the microchannel. So if I go back here to like these types of flows where the flow is indeed laminar. So we have looked at these things also with Fluent, and there we use laminar flow models to look at the liquids, the liquid flow. I will say, but that's probably beyond the scope here. But there is a paper available if you're interested in looking at these things. So you can actually see some. I wouldn't call it turbulence, but there are some instabilities that you can generate downstream of these structures. And so that's why we've chosen the structures to be alternating in this way, because we found that you can actually generate some beneficial recirculations downstream of these structures as well. But again, that was all done with laminar flow modeling. That was not with turbulent modeling.
Yeah, thank you.
Tim, do you understand well that Ireland is so good for data centers because of a combination between climate, cold enough, taxation, and maybe, I don't know, because it's really very successful. 14% of the total electricity in a country for
Yes.
data centers is huge. And I mean, at the end, you are going to have 100 data centers in the country. Why is this so successful there?
Yeah, that's a good question. It's a combination of those things, like you say. The climate definitely helps. It's a maritime climate, so our winters are quite mild, our summers are pretty cool. So we have a relatively stable temperature. Average temperature is 10 degrees averaged over the year. But a large part as well is corporate tax law. So Irish government is quite aggressive in Europe, and they often come under scrutiny from the European Commission, in fact, that their tax laws are too aggressive in getting companies to locate their data centers in Ireland. And so there's actually quite a bit of pushback from the local population on that now as well, because we have very low tax rates. So a lot of these big companies like Google and Facebook, they have their huge data centers here, but there's only very limited taxation, so money that flows back into the economy from their presence. So a lot of the population see this more as a burden nowadays, because they consume a lot of electricity. So it means that the electricity supply is under stress at times. And of course, Ireland being an island nation, we have very poor connection of the electricity grids to neighbors. We have some connection to France and to UK, but it's we're sort of an island, so we have to make sure that our grids remain stable. So we can't really go to full renewable energy, for instance, because of the presence of these data centers. So
Okay.
there's a lot of
Yeah, there are,
advantages and disadvantages.
yeah. May I have a very short second question? Is about the fact that a lot of people are speaking about immersion cooling, no? For also even for data centers. I remember that the one very old Cray was already, the supercomputer Cray supercomputer was cool with this solution. What do you think about immersion cooling for data centers?
Yeah, that's definitely an option. We don't really see it as yet. So if you look at the prevalence of modes of cooling, air cooling still is the dominant form of cooling. immersion cooling definitely would be beneficial from a point of view of waste heat recovery, but the investment cost is huge, and not just investment cost, because these fluids, these dielectric fluids, for instance, are quite pricey. So taking that into consideration and the investment cost needed to build a new facility is apparently too much nowadays. So people still will go to air cooling. But also the maintenance is more complicated, because you typically have to maintain some of these things. They will fail, so you have to pull them out of the liquids. A lot of extra hassle involved in doing that.
Right.
Yeah.
Yeah, it's true. So maybe there is a last question, and then we need to stop. Yeah, the last, only one.
Hello.
Yeah, please, there. Please,
So my question is, in the assumption you made, baffles. Can you move to the baffle slide number 36? Yeah, this is okay. Last, before that. This one. Yeah, here assumption is made that liquid cooling with CPUs, liquid cooling is done. So in the numerical model, don't you need to take that liquid cooling section? At least it is as a solid.
Yeah, that's a good point. We've decided to ignore that, because our CFD model is a 2D representation of the flow. So we wanted to have a very simple model that we could have the most efficient CFD model possible to use in our numerical optimization loop. So we've decided, because the cold plates, the liquid cooled cold plates, are typically very they're not very high. They're maybe a centimeter, let's say, maximum. So for the most part, that means that the air can simply flow over them, and it doesn't really pose a lot of resistance to the flow, no more than any of these downstream heat sinks would, for instance. So we've decided we'll just make it as simple as possible, and we'll simply ignore the presence of these cold plates. But you're correct. Yeah, if you wanted to be more accurate, you would want to probably introduce some of these extra components to get a better sense for where how the air would move through the system. It's mainly just a side effect of being a 2D simulation. So we didn't want to have a large pillar here blocking the flow, because in reality the flow would be able to flow over these cold plates anyway. So and certainly thermally they don't really contribute anymore, because we assume that the heat from these CPUs is absorbed directly in the liquid coolants, and no longer a problem, let's say, for the server.
Oh, thank you, Tim. I think we have some more questions, but then we are running short of time, and we are already into the next presentation by Professor Polycockos. So, we thank once again Professor Tim Persoons for a very interesting talk on electronics and data center cooling. And as a token of appreciation, we would like to ship a small memento across to you. Maybe you can send the address where you want this to be shipped, and we will do that. And we look forward to continuing the interactions in the future with you. Thank you so much.
That's great. Thank you very much.
Thank you. Bye.
Thank you.